So we just got done talking a little bit about how the conjugate acid or base that's produced as a result of an acid-base reaction is the thing that actually dictates the acidity or basicity, or ultimately the pH of that solution. And so I want to add a little bit of nuance to this and think a little bit about what about metal ions and how do they react with water? Because we haven't really talked about that in your chemistry experience thus far, but it turns out that metal ions aren't maybe as innocuous as you once thought, and they can actually change the acidity or basicity based on this process called hydrolysis. So let's think about this metal ion. This is aluminum 3 plus as our starting point because it has a fairly extreme type of hydrolysis reaction with water. So if you see something written up here like this, aluminum 3 plus, aqueous meaning it's dissolved, you might just assume that aluminum is hanging out in solution, no big deal, nothing's happening. But in fact, there is something actually happening. So at the beginning of this class, we talked about how things dissolve and the balance of intermolecular forces that are required to get something like this to be solvated. And by solvated, we mean the polar nature of water orients itself to stabilize in sort of a cage that we call a hydration sphere. So for aluminum, that hydration sphere kind of looks like this, where you have actually 6 of these individual water molecules traced around this thing, and they're all being stabilized with the most electronegative atom, the oxygen atom, positioned closest to that positive charge. And that should make sense from an intermolecular force perspective because now you have this ion dipole interaction that's net stabilizing. That's a happy place that's stabilizing this system. And those intermolecular forces that are stabilizing the aluminum ion, I've highlighted here. Those aren't real bonds in the sense of the covalent bonds holding hydrogen and oxygen together, but they're forces that are net stabilizing based on the electrostatic differences, the positive and the polar negative charge on that oxygen. So the immediate implications of this are that metal ion here, the aluminum ion, it's actually kind of, you can imagine it like it's sucking the electron density, right? Each of these water molecules has an electron cloud around it. And because it's really positive, it's 3 plus, it's really drawing or sucking that electron density towards itself. So you can sort of think about that as this net draw where there's this pull towards the center, and electrons are getting yanked towards the middle there. So these green arrows, if you remember this back from Chem 107, the arrows with the little hash sign represent the dipole or the polarity direction of a molecule. And wherever the hash is, that's the more positive part of the bond. And where the arrow is pointing, that's where more electron density is existing. And so it's really just indicating the same thing I said in words, that sort of the tips of these water molecules out where the hydrogens are, that's going to be more positive than normal because it's sort of pulling the cloud inward. And that creates a consequence here where these outermost hydrogens are partially positive. Remember this little Greek delta sign, partial positive, partial negative. And since these are more positive than a normal water molecule just floating around the bulk water solution, it makes them more vulnerable to be snatched up by other things. The other things in the solution are just all the other water molecules that are out there in solution. So if I have this sort of example water molecule that's not associated with the aluminum, but it encounters this hydrated metal ion in solution, so it means it gets pretty close. All of a sudden it starts to see these waters, which are unlike all the other waters in solution, because these protons are maybe easier to grab. In other words, these protons are more acidic. They're easier to donate to water as a base than they are by themselves because, remember, this little dash here, that's 2 electrons. And if those electrons are being sucked inward towards the metal ion, then it's pretty darn easy to come in and just snag that. And so what that looks like is just these electrons essentially come in and grab that thing. We can kind of make an arrow, and this is the actual formalism you would use in an organic chemistry class. This is really all organic chemistry is what we call arrow pushing, where you take the electrons and you say, I'm going to grab that thing and form this new. So what that means is now, is if we draw this sort of as a reaction, that original water molecule now has this new bond here because of those two electrons. It snagged it off of that one. So we have a hydronium ion. This is H3O+. That's what it would look like. Plus, we have this whole metal ion complex, which had 6 waters to begin with, but now one of those waters is absent a hydrogen, which means it's now an OH, or a hydroxide. So how would we write that up? So that complex, that hydrated metal ion complex would look like this because we have aluminum, and normally we would have 6 of these waters, but we snagged one and converted it to hydroxide. If we're grabbing a hydrogen off of here, conserving those electrons, then we've made OH minus. And so the net charge on this whole complex is now 2 plus instead of the original 3 plus, because this OH has a -1. So 3 plus, -1, makes 2 plus. So let's write out this full reaction so it's clear. So the full reaction, sort of in a cartoon scheme, so it's clear to you, looks something like this, where we have the original aluminum 3 plus. You can see that electron density being pulled towards the center, making one of those water molecules kind of vulnerable. Then we have a water come in and snag or act like a base, grabs one of those protons, and now we have a new complex which looks almost the same, except we have one of those waters as OH. So it started out as a aluminum with 6 waters. We call that's a metal hexahydrate, or aluminum hexahydrate because of the 6. Reacts with water as a base, now makes aluminum pentahydrate with a monohydroxide. The overall net charge is now 2 plus, and we have the hydronium. And since we've produced hydronium ion in solution, if this is the net solution, what would we predict the pH of this system to be? Well, if we add more hydronium to the solution, then we would expect this to be acidic, and that's true. So metal ions are considered acidic often if they are capable of driving this hydrolysis type reaction, because essentially they're acting like acids. That one of those water molecules, that hydrogen bond, it starts to weaken because of that electrostatic pull, and it donates a proton to H2O, which acts as a base. So this really acts like an acid.